from the form of the impedance that we ended up talking about earlier, that it's important to remember that we said that the power delivered to inductors and capacitors by alternating current is zero. So there's no power whatever that gets delivered to either one of those. So in order to end up having the most efficient production of power, we want to end up having the effects of your inductor and capacitor to end up canceling each other out. And from the form of your impedance equation, again, like I said, I didn't explicitly do the derivation just because it takes a lot of time, and I don't think it will be terribly informative to see it. But because of that form, if your inductive and capacitive reactances are equal, if you look back at the formula, that your impedance will be the square root of r squared plus the difference of those squared. So if the smallest number a square can be is 0. So if you end up causing the square to be 0, that means your inductive and capacitive reactances have to match. And so we'll end up taking a look at when that happens. And that occurs if we go back to the equations, that your inductive reactance is 2 pi times the frequency times the inductance. The capacitive reactance is the reciprocal of 2 pi times the frequency times the capacitance. So if we set those equal and we do a little algebra, we end up getting that the resonant frequency is 1 over 2 pi the square root of LC. And this specific frequency is called the resonant frequency. So in terms of what does it mean for something to be in resonance, it means a whole lot of different things. It means that your inductive and capacitive reactances are the same number. It means that your impedance is equal to your resistance, which is the smallest number it can be. Your RMS current will equal your voltage divided by the resistance, as opposed to, in general, it's the voltage divided by the impedance. And that your average power is always equal to I RMS squared R, but then in this situation, since from the formula your impedance is minimal, so your current is maximal, which ends up meaning that the average power is maximized when you end up doing that. In general, if your inductive and capacitive reactances are different, your average power is multiplied. It's your voltage squared over resistance times the cosine of that phase angle, and so cosine of the phase angle is called the power factor. It's by what percentage you're lower than the maximum amount of power you could deliver for your voltage. And notice that you're having to provide all that extra current. So one of the reasons why you end up seeing in any kind of a factory or whatever like that, you'll always have a box outside with warnings out there saying that high voltage or whatever like that, and there's this box, and what's inside that box is a set of capacitors. And the reason why you need them is because the inductor coils inside, because remember we talked about the other day that you need to have inductor coils to run motors. So the capacitors are then out there in banks in order to end up making sure that you end up having resonance between your capacitors and your inductors. And that's because if you don't, then the power company is going to get upset at you, because not only does that cause some other secondary effects which are also problematic, but it also means that you're drawing current, and since your meter is measuring basically the power delivered and not the product of the current and the voltage, which is what the power company actually has to send, then they're not getting paid all the money that they were for all the current that you're drawing, which is not going to end up sitting well with them and end up causing problems. That typically because these sometimes get not perfectly imbalanced, but if your power factor is is less than about 90%, then you're going to end up getting a phone call. So and they'll have words with you, So it's not good. All right. The If you end up having alternating current, whenever you end up saying, if you see a number just for your alternating current source in volts, that number always means the voltage. It's never the maximum potential difference. And similarly, you'll end up seeing you don't almost ever see your frequency written as angular velocity. It's always written in hertz. It's the frequency. So that the power supply that's running the computer that I'm on right now will be 120 volts, 60 hertz, which is standard internal one for not higher voltage things like maybe a washing machine. For regular power at your house, that'll end up being what it is. And the frequency across the United States is standardized as 60 hertz, and it's basically maintained as being 60 hertz plus or minus a few thousandths or so, and it oscillates a little bit from time to time, but it's effectively all very, very close to 60 hertz. So then I gave a couple of examples. So find the power delivered in that particular circuit. I've got 160 volt, 6 and 800 hertz AC source, 4,000 ohm resistor, and if it looks kind of funky the way I wrote it, it's because I started with 40 and I realized if I did that, then the numbers are not going to be the capacitive reactance is going to be gigantically more than the resistance, so I wanted to make it a little bit more balanced. So I made it 4,000 ohms and in series with 24 nanofarad capacitor. So your average power is your voltage squared over resistance times the cosine of your phase angle. So the trick there is figure out what your phase angle is. Find your phase angle. It's the arctangent of your inductive reactance minus your capacitive divided by your resistance. Because there's no inductor at all, your inductive reactance is 0. So again, if you get a problem like that, that's how you deal with it. So then calculate your capacitive reactance 1 over 2 pi FC. Only thing to be careful on here, sometimes we didn't have to end up putting in your units, finding any of these things in this one for your reactances. If you're needing to calculate, as we'll talk about later, what capacitance you need to be in resonance, all those things you do have to include your powers of 10, so make sure that you have those in there. So I computed that my capacitive reactance in this circuit was 8,289 ohms. So then your phase angle is the arctangent of minus in that case, your capacitive reactance divided by your resistance. And then you end up calculating your average power. And this one was about 2.8 watts. So that's how you'd end up finding that. So that shows you also in the same question, if you're needing to find what is the value of your phase angle, that gave you an example of how to do that too. All right, so the next piece that we'll look at here will end up being how antennas work and what gain is. So whenever you end up having what an antenna is in terms of a receiving antenna, you'll end up having an inductor coil, and then you'll have that in series with a variable capacitor. And we talked about way back when, but it may have been a while to remember. Remember the capacitance for an air-filled capacitor is your dielectric constant will be filled with air in this situation, so that's basically 1. So your dielectric of 1 times epsilon 0 times your cross-sectional area times the D between the two. So what's easy to do is to end up having a screw that will end up causing the distance between the plates to change. So this allows you to vary your capacitance by varying that denominator in in your capacitance. So then that allows you to tune the capacitance. So if you're talking about tuning a radio, if you've heard of that, then that's what you're talking about. That's how you end up doing it. In order to receive the signal, though, you end up having to have the signal come into the antenna, and there are really two different general ways of doing it. That the details of how antennas work and really can be a lot more complicated. Just the really, really, really simple idea. One of them can end up basically just being a piece of wire that goes up and down, and the other one will end up being where you have a loop of wire like this. So if you've ever seen a set of rabbit ears, that's probably the easiest way to remember to understand it. So you got your rabbit ears doing this stuff. So that's the straight type. When you have the one that you can spin around and do this stuff, that was the loop. For a straight line, what's happening is with electromagnetic radiation, and we'll talk about that one in the next section. Electromagnetic radiation is oscillating electric and magnetic fields. And so what you'll end up having then, if you have a piece of metal and you have electric field from the outside impinging on it, then the electric field will cause charges inside of your conductor to start to move. So you end up getting a potential difference due to that, and the potential difference is oscillating because the electric field is. So then you end up having that thing then feed into the rest of the circuit. For the one that would be a rounded one like this, where you got the bottoms connected to the wiring, then that's where you have your EM, the magnetic part of your EM radiation is oscillating through the loop where we talked about before. That's going to end up inducing an EMF due to a change in your flux, magnetic flux through the loop. So you end up getting a potential difference that way. So either one of these things, then you're producing an alternating electromagnetic field, electromagnetic force, electromotive force. So that's going to effectively be your source. However, you also are going to have lots and lots and lots of different EM radiation coming in all the time. So you've got light that's coming in. You have X-rays from cosmic rays happening. You've got infrared from the local heat around you. You've got radio waves from all kinds of different sources. So the other thing that you have to do in order to make it useful is to be able to tune what frequency you end up getting current through while getting very little current that would be from one that's close in frequency. So I ended up giving an example, and the one I gave actually probably had too high an inductance, so your capacitance looks really super tiny. But again, this is an illustration. Suppose we ended up having a piece of wire with a resistance of 50 milliohms in series with and that I said it was 50 milliohms for that, but it's 50 milliohms for all the wiring, is assume understand that that would be in series then with a variable capacitor, and I had an 81 microhenry inductor. So in a real one, you're going to get a smaller value than that. So in this situation, our variable capacitor, if we're wanting to tune in to ABAC radio at 103.7 FM, 103.1 FM, what we're wanting to do is to get a lot of current at 103.1 FM, but to avoid the ones at the FCC allowed next interval above or below, and the FCC allows for another station to operate 2/10 of a FM unit, and FM units are in megahertz, in millions of hertz. So it can end up being just that close, and you could have another station, and you're trying to make sure you get this one and don't get that one at very much current. So we first end up finding at resonance what capacitance you need. So I ended up showing you how you do that, and I used the formula derived earlier. So otherwise, you could go back. Your resonance frequency is 1 over 2 pi square root of LC. So you rearrange that, you get that formula for your capacitance. And I found that it was actually 29.4 femtofarads. Don't worry about the femto unit. It's 0.0294 pico. So then, in order to describe the amount of gain, that's how effective your antenna is for separating one type of frequency from another one that's close. It would end up being the ratio, if you have the same voltage, the ratio of the current at your resonant frequency, or the one that you want, divided by the current at the frequency you don't want. So you can end up calculating that. Then I showed you at resonance, it's just your delta V RMS over your resistance. At whenever it's the other one, it will be your delta V over your impedance. So if you rearrange that, that gives you the impedance at the frequency you don't want, divided by the resistance at the frequency you do. So at 103.3 FM, because that's the one we don't want, you'd calculate your capacitive and inductive reactances. So I showed you the capacitive reactance was 52,405 ohms. Your inductive reactance 52,573. So then your impedance we calculate is the square root of R squared plus XL minus XC squared. So I got an impedance of 168 ohms. And then, so the gain was that ratio, 168 ohms, divided by your the impedance at resonance, which is just the resistance at 0.050 ohms. So that gave me a gain for that antenna of 3,365. Then at the beginning of the next one, there's another small topic with alternating current that I'll end up appending to it. And it's really, really easy, so I wanted to give you something that could be an easy question. That we'll end up talking about how transformers work, and so we'll end up doing that, and then we'll end up going into what electromagnetic radiation is.